Luckily, this was the first such event bright enough that astronomers from the University of California, Berkeley, could study the optical light from the stellar death, specifically the light's polarization, to learn more about what happened after the star was torn apart. Their observations on October 8, 2019, suggest that a lot of the star's material was blown away at high speed, up to 10,000 kilometers per second, and formed a spherical cloud of gas that blocked most of the high-energy emissions produced as the black hole gobbled up the remainder of the star. Earlier, other observations of optical light from the blast, called at 2019 QIZ, revealed that much of the star's matter was launched outward in a powerful wind. But the new data on the light's polarization, which was essentially zero at visible or optical wavelengths when the event was at its brightest, tells astronomers that the cloud was likely spherically symmetric. The results support one answer to why astronomers don't see high-energy radiation, such as X-rays, from many of the dozens of tidal disruption events observed to date. The X-rays, which are produced by material ripped from the star and dragged into an accretion disk around the black hole before fall. This observation rules out a class of solutions that have been proposed theoretically and gives us a stronger constraint on what happens to gas around a black hole, said UC Berkeley graduate student Kishore Patra, lead author of the study. People have been seeing other evidence of wind coming out of these events, and I think this polarization study definitely makes that evidence stronger, in the sense that you wouldn't get a spherical geometry without having a sufficient amount of wind. The interesting fact here is that a significant fraction of the material in the star that is spiraling inward doesn't eventually fall into the black hole. It's blown away from the black hole. Polarization reveals symmetry. Many theorists have hypothesized that the stellar debris forms an eccentric. This was not observed for this tidal disruption event. One of the craziest things a supermassive black hole can do is to shred a star by its enormous tidal forces, said team member Wenbin Liu, UC Berkeley assistant professor of astronomy. However, due to the extreme computational cost in numerically simulating such events, astronomers still do not understand the complicated processes after a tidal disruption. A second set of observations on November 6, 29 days after the October observation, revealed that the light was very slightly pole. Both observations came from the 3-meter Shane telescope at Lick Observatory near San Jose, California, that is fitted with the CAST spectrograph, an instrument that can determine the polarization of light over the full optical spectrum. The light becomes polarized, its electrical field vibrates primarily in one direction, when it scatters off electrons in the gas cloud. With each of these processes, the light loses some of its photon energy, going all the way down to ultraviolet and optical energies. The final scatter then determines the polarization state of the photon. Only more measurements of the polarization of light from these events will answer that question. Polarization studies are very challenging, and very few people are well versed enough in the technique around the world to utilize this, he said. So, this is uncharted territory for tidal disruption events. Patra, Filipenko, Liu and UC Berkeley researcher Thomas Brink, graduate student Sergei Vasilev and postdoctoral fellow Yi Yang reported their observations in a paper that has been accepted for publication in the journal Monthly Notices. An optical glow from hot gas emanated from a region at about 30°. The 2019 spectropolarimetric observations, a technique that measures polarization across many wavelengths of light, were of at 2019 QIZ, a tidal disruption located in a spiral galaxy in the constellation of Eridanus. The zero polarization of the entire spectrum in October indicates a spherically symmetric cloud of gas. All the polarized photons balance one another. Research at Lick Observatory is partially supported by a generous gift from Google. A major upgrade, led by Brad Holden, of the CAST spectrograph on Lick Observatory's C. Donald Shane 3-meter telescope was made possible through generous gifts from the Heising-Simons Foundation, William and Marina CAST, and the University of California Observatories. Monthly notices of the Royal Astronomical Society, 2022, doi. 10. 1093, MNRAS, Stack 1727 University of California, Berkeley. https://ift. TT, 4BAPDJO. Access July 11, 2022. Thanks for watching. Please subscribe my channel for more videos.